Hello everyone, welcome to my channel. This is Simon. Recall that at the end of last video, I talked about an example with regard to the practical applications of a series with regard to moment generating function, namely the uniqueness of moment generating function. I said that it is very important and useful in some practical usages, and one of the examples will be prove that the chi-square distribution is actually the sum of n independent, identical standard normal distribution. The square of these distributions add up together, they will become a new distribution called chi-square distribution. And in this video, I'm trying to explain the procedures on the provement of this statement. And we should apply the uniqueness of moment generating function in order to prove such a statement. Before that, let me just briefly go through the definition of chi-square distribution. So basically, if there is a gamma distribution, I think I have a video talking about gamma distribution and its moment generating function. It's in my playlist, and you can check it if you wish. So if there is a gamma distribution with alpha equals to v over 2 and beta equals to 2, and the moment generating function of a gamma distribution, it takes the form like that. I have proved it in previous videos, so just check it. And you just substitute this alpha and beta with the detailed numbers, numerical data, and then you can find out the moment generating function of a chi-square distribution. What is it looks like. And then we just define such a distribution, chi-square distribution, with v degrees of freedom. And you see it's just a special kind of gamma distribution with alpha equals to v over 2 and beta equals to 2. And then you can find out the moment generating function of the corresponding distribution. It takes the form like that. And so the next step is to move forward to the right hand side of this equation. What's the moment generating function of such kind of distribution? The sum of n independently identical standard normal distribution, the square of them added up together. What is the moment generating function of this distribution? And we will compute the moment generating function in the following procedures. We call such moment generating function phi, and we want to know phi takes the value at z1 square plus z2 square up to zn square. Well, this turns out it is the expected value of Euler to the t times a bracket. Just substitute in. Takes replace the original position of x. I mean, if you take moment generating function in respect to x rather than this lengthy formula, then it can be expressed as the expected value of Euler to the tx. This is, I guess, yes, it takes the value like that. And then you just substitute and replace x with this a little bit long formula. And from this step to this step, this is a inner manipulation. Whenever there's a sum added up on the power of a such kind of function, it is equals to the product of the separate segments times together. And then by independent property, because we have assumed that these n distributions are independent, you can take the product out, and each of these are just one single segment of the moment generating function of zi squared. And through this way, we reduce the question to find out the moment generating function of one specific z squared. And it's not hard to proceed. You just take the integral of the probability density function of a standard normal, and then times with Euler to the tz squared. Put all this inside a integral, and then you just add up the similar terms like that. And here it requires a little bit of wise substitution, because later on in the proceeding with the formulas, we would like to see something like Euler to the minus u squared over 2, because this is a standard form of a standard normal. And then you can take advantage of this, bear in mind, and the consequences let u equals to the square root of this bit other than this minus sign. And then if you square it, it is exactly the same thing with the original integral. So once you have set up such a formula, you just find out what is du and substitute back to the integral. And then you can find out one single moment generating function segment for zi squared, arbitrary 1 zi squared. And since you know that the final result we are going to find is just to make the products of this n moment generating function, and then you will just raise this result up to k's power, and you will see that it takes the same form as the chi-square distribution, the definition of chi-square distribution. And by doing so, we can finally conclude that these two distribution is the same. And we can then say, okay, chi-square is equal to z1 squared, z2 squared, sum up to zn squared. And we have ended up the proof. And that's it for this video. I shall stop here. Thank you very much. Goodbye.